The cutting plane one, you should. You just did the homework, right? What about the branch and bound? Is gone? What's still there in our head? It's gone? So what I plan to do, what I did in the other class was that I went through 2 examples, very detailed. One was the one we did last time, but I went through it again at the same time, solving it in LP Assistant. So that's what you will have to do for homework, so you know what you have to do. And then I did another example, carry out the same thing, just to reinforce, because if you know where to click, it's very fast, but you really need to know where to click and what to do. Does that sound like an okay plan? Then there was a little time left to go through the next chapter. So let's do that. So what I will do, I will put the problem here, and then we'll draw the diagram on the other side, and the screen will come down in the middle, all right? So this problem, maybe I don't have to do it, but let's put this up. This is from last time. I want to minimize z x1 minus 2x2 subject to 2x1 plus x2 less than half. Less than 5. So that was the problem we went through last time, with me just writing out, you do this, you will get that, you do this, you will get that. And today we're going to fill in all those, you do this and how you do those, all right? So adding this to the problem makes it so much more complicated. Without that, you have the simplex. You click a couple spots, you're done, right? But with this, you know you're not done. There's a lot more to be done. Okay, so what we will do will be, I will show you just how to carry all these out in simplex. So will the screen be visible with the light on the chalkboard on? Because I need to be able, would that be okay? We'll see. If not, I'll turn it off. All right. Documents. I have the LP Assistant here. All right, so this problem should have 4 variables if I add flex, what do you call, slack variables. So I have let's punch in those numbers. So this is how you will do for homework. You have problems like this, and then you have to show me all the tableaus that you use to generate this problem, okay? -4, 4, 1, and 5. Is that right? These are the constraints, and your objective function is 1, -2, right? Did I type? I did the same thing in the last class. What's wrong? Exactly the same thing. 4, -4, 5. Okay. Now it's correct? Any mistakes? Let me know. So I declare the basic variable, the slack one that I add. If any step you don't understand why I'm doing this, stop me and ask, okay? Because it builds on. There's so much that comes. It's a bit overwhelming. Okay, now let's pivot. So right now I use the regular simplex. I find a negative coefficient here. I check the ratio, 1.2, 5. So I click here, right? And then I have another negative one. I check there's only one positive. I click here. Is it all clear? And now they're all positive, which means this is the minimum, the negative, this is the minimum attained at these places, which are not integral, right? But I solved it. That's the first step. Neglect the integral condition and solve it. So, okay, so I'm going to collect the information here. So first step, maybe a bit skinnier because I I don't have, it's not very long here. So what do I get? The z min is negative. Negative of that, for 15 over 4, you want to rewrite that number as the integer plus a proper fraction. You need to know what is the integer there. Is that okay? That part you have to do. So this gives me 3 and 3 over 4. So it's this 3 that's important, okay? It's 3 point something. And x1 is 1 and 1/4. You want to do that also. Actually, you just need to figure out 1 point something. x2 is 2 and a half. That's the first step. Okay. So before we move on, let's look at it and see if we can find any bounds on the solution. So this is telling me that if I solve the original problem neglecting the integral constraint, I get a minimum at -3, 3 over 4. What does it say about the actual minimum? Can the actual minimum be even smaller than that after I restrict it to only integers? It can't, right? If I restrict to integers, I would shrink my feasible region, and the optimal value will be worse, not as good, right? So here we are minimizing. That means the actual minimum for the integer linear programming problem would be bigger than that. What is the smallest integer that's bigger than that? Is -3. Is that right? So you should know that. Actually, the mean should be bigger than -3. So this is the bound. One bound you have on your solution. You keep track of it next to the table. All right? Now I see that both x1 and x2 are fractions, so I branch out. I can pick either x1 or x2 to make the following problem. It's random. Let's just pick x1. So x1 lies between 1 and 2, so I exclude x1 in my solution. That cuts it into 2 regions. One is less than 1, the other is bigger than 2. Is that clear what we're doing? Okay, so let's draw a block here. I'll put the answer here, and I'll put the answer here. Okay. So if you are using LP Assistant, like when you first open the LP Assistant, it gives you a number for the problem. So this is problem 1. You might want to keep track of those numbers. So I will put in 1 next to this, say that comes from tabular number 1. Question?
Could you have also picked x2?
You could, yeah. Either way is fine. You should lead to the same minimum value. Yeah, but the procedure will be different. You'll take different paths. The branch will be different. Yeah. Okay, so you want to keep track of all these tableaus that's being generated. So let's say this one will be the second tableau I use, and this will be the third one. So just to help you keep track of things, all right? Otherwise, you will see later on, I will open so many of them, it will be really confusing if you don't keep track. Okay, so now I make a new problem from problem 1. That will be my problem 2, where I add the constraint x1 is less than 1. Is that right? So you need to go and add it. So you need to add that constraint, which will give you one more equation. So new, add a constraint, and then I would add a regular variable, because I need to add a slack variable to deal with the inequality, right? So x1 will have 1 here. Slack variable is 1. It is less than 1. So that's the new constraint you add. Is that clear? And then I see that the slack variable here serves as the basic variable. Is it all clear what I'm doing? And then after adding this on here, I see that the x1 here is no longer a basic variable. It needs to be pivoted further because I put a 1 in this column, right? So you have to remove this from the basic variable set. Is that clear? All these you have to do without making a mistake. Okay, now I can go pivot. So the first step of pivot, you're not doing anything. You're just claiming back the basic variable x1. Is that clear? I will click here. So now x1 is the basic variable. Basically, it made that 0. Okay? And now watch. The new equation you added, the new constraint added, has a negative b on the right-hand side. It has to happen. If you don't get that, you did something wrong. Go back and check. Clear? Now what do we have to do? It's not the regular simplex. I need to go to the dual simplex. Is it clear? Okay, and then I check this row and see if there are any negative coefficients. There's 1, so no doubt I click here. All right? And now I see they're all positive. So I found the optimal for this problem. Okay, and let's record it. So the minimum is 3.5. So z min negative 3.5. Let me just write decimals. x1 is the y1 is 1. x2 is 2 and 1/4. Okay, so we'll leave that there, and we need to solve the other branch. Okay, the other branch is x1 bigger than 2. Now be careful, you need to go back to problem 1. It's from there you generate this branch, right? So click on that. So problem 1 is up, and then you make a new one from problem 1. That will be problem 3. Is that okay? All right, so go back to edit, and I need to add a constraint, add a variable. All right, so now is x1 is less than 2. It's the same as negative x1 is less than negative 2. And then I add the slack variable. Is that clear what we do? And that slack variable now serves as a basic one. What should I do before I click edit? I need to remove x1 because it's not a basic variable. Remove that. Clear it. Is that okay? Okay, now let's pivot. So first step, I claim back that I want this to be the basic variable. Okay? And then you see it always happens. The new equation will now have a negative b on the right-hand side. Otherwise, you did something wrong. Okay? Now I go to the dual simplex, and then I see actually there's only one negative. I can just click there. The dual simplex only tells me the ratio, right? I'll click on that, and then I get all integers, don't I? That's nice. So let's record. So the minimum is 0, is obtained at integer values. So z min is 0, and x1 is 2, x2 is 1. So it tells me that I have found an integer solution that is at x equals 2, x1 2, x2 equals 1, the z attains value 0, right? So this gives me another bound. It says that the minimum has to be, so this gives him another bound. The minimum is, can you guys see behind this over there? The minimum is bigger than negative 3, and it has to be less than 0 because it can't attain value 0. It has to be lie between these two. So I have another bound. Okay, those information you collect alongside with you. Okay, now keep in your mind, if you have a problem and you choose to branch out of this problem, make 2 more problems. So this has a minimum negative 3.7. And you see this minimum here is negative 3.5, and that's 0. Those two are both worse than that. And that has to happen. Is that right? Because you shrink the feasible region into smaller ones. If you got something negative 4.5 here, then you did something wrong. That can't happen, right? Okay, so now this is an integer solution. It's bigger than -3, and I don't know if it's optimal or not. So there's no reason I should branch further out from there. But this one gives me -3.5. I hope that I branch out from here, I could get a minimum that's probably even less than 0, right? So that's the reason we branch out here further. So I will choose to deal with x2. So this will be x2. It's between 2 and 3, right? So less than 2 and x2 bigger than 3. These are disjoint constraints you put up. Okay? And let's put a block here and a block here. Okay, and then I know in the LP system, this will be table 4, this will be table 5. Okay, I label them. Keep track, otherwise it's really confusing. Okay, so I need to go back to problem 2 and branch from there. Is that clear? So I look for where's 2. That one is hiding behind. So you need to find out that tablet for problem 2, and then make a new one from there. Is that clear? Okay, and then the one on the left will be adding x2 less than 2. So I will add a constraint, add a variable. x2 is less than 2, and that's a slack variable that I add. And the slack variable will be the basic, right? What should I do before I move on? This guy here is not basic variable. Is that right? I have to remove it, clear that. Is that okay? All right, now I go and pivot. So first step of pivot, I claim this one back to make a basic. And then you see, it always happens. The new equation you add now has a -b on the right-hand side, okay? And then I am in the dual simplex mode. I need to choose between this one and this one. So that's -2, that's -1. I should choose the -1, right? Come down. And then now you see it's all positive. So I found the optimal solution. Let's record it. So it's 13/4. That's 3.25, right? So Z min is -3.25. X1 is 3/4. X2 is 2. So you see, I made x2 integer, but now x1 is messed up. This happens. You will have to go back and forth, all right, before they both turn. And I know that is not done because it's -3.2. It's less than the bound that I obtained there. I could probably further branch from that. Okay. Now let's do the other half of this branch, starting from problem 2. Make sure you choose the right problem to start with, and then I make a new tableau. Okay. So here, go to editing mode. I will have to add a constraint, add a variable. Is that okay? So what do we add? x2 is bigger than 3, meaning -x2 is less than -3. Is that clear? And I claim the y6 to be the basic variable there. So what do I do now before this y2, x2 here is not basic, right? Now I can pivot. Okay, so first claim this basic variable back. Now I have a nice set of basic variable. Oh, did I do something wrong? That should be 1. Why did I put -2? That's -1. Because I was saying an x2 now. Okay. All right. It's good because I saw something was wrong because the b was not negative, right? So, yeah. Okay, so at least I did not blindly continue. And now it's negative as expected. Now I would use the dual simplex method, and I would try to pivot at somewhere that is negative, but they're all positive. So what does that mean? What did someone say? Someone say something here?
Not feasible.
Yeah. There's no feasible solution, right? Remember? So this one is actually not feasible. So meaning that after putting up this constraint, you cut out the whole feasible region. It's empty now. There's nothing left. Okay, so that's no good. Okay, but then this is still no good, so I have to branch out further. I choose this one to go further out because x1 now is a fraction number. It lies between 0 and 1. So I should have x1 less than 0, but x1 cannot be less than 0, so it must equal 0, right? That's the only possibility. And the other will be x1 bigger than 1. Is that clear? Why it become equal? Because everything is non-negative here. I don't go to the negative region. Okay? So let's label 4, 5. So this will be 6, and this will be 7 in your LP assistant to keep track. Okay, so I need to go back to table 4 now. Where do I find you? Table 4. There you go. I need to go back there and start a problem from table 4. So you go to problem, say new from 4, right? That's the problem 6. And for the problem 6, what do? We add x1 equals 0. So I just need to add a constraint. I don't need to put another slack variable because it's equal sign. Is that okay? So it's equal. So this means x is 0. And that's all. And then I know this is not basic variable because it got messed up. Okay, now I need to pivot and get the basic variables correct. You have options. You can do what you like. Let's pivot here because it's all 0. So it will only make that guy disappear, make it 0. Let's say I click on that. And then I still need to set a basic variable for the first equation because right now it's not canonical. So let's say I click on the 1 to hope get better number, okay? I pivot over there. Okay, now I have it in canonical form, and this is all positive. So it's done. After putting it in canonical form, it is giving me the optimal already. All right? So let's record. So what did we have? So that's 2.5. That's my minimum. So Z min is negative 2.5 at x1 is 0, x2 is 5/4, 1 and 1/4. Okay, and we have the other problem to solve before we can conclude. Now I have to find problem 4, which is here. Choose that one and start from there. New from problem 4. Okay, and let's move this a bit up and let's edit it. So I need to add x1 bigger than 1. I need a constraint. I need a variable, right? So it's like negative x1 is less than negative 1. Is that right? And this will be the basic variable. This is standard. And this one here is not basic anymore, so clear that. Okay? And then we go and pivot. So first step, set this basic variable here by step of pivoting. And then the added equation has a negative on the right-hand side. Right? If you added inequality, this always happens. Okay? So it's a control for you to know. And then I see that there's only one negative number I can click. So it's clear that I have to click here. Look at these nice integers. That's where you smile. It's happy. Ha! Maybe I'm done. Let's put it down and look at it. Where are my chalks? So exciting. Okay. So what does it tell me? C min is -3 from the table. I see, right? Obtained at x1 is 1, x2 is 2. Okay, so I claim now this is the optimal solution. Because, could you give me an argument why I could claim that? Look at the information we have collected on the bound, on the minimum. What is the best, the smallest minimum I could hope for? -3. Did I get it? Yes, I'm done. I cannot do any better. It can never be -4, right? Is that clear? Okay, because you're bound, because of the bound that you have, you know the mean has to be bigger than -3. That's why. Then you're done. Is that clear how this is carried out? Would you be able to do it? Not the most impressive algorithm, isn't it? It's so time-consuming. And keep working out. Okay. So now I plan to go through another example just to solidify, because it is a bit confusing, all that, what you have to do. So I will put the next problem there, and then we'll draw the tableau over in that corner, all right? So let me write the new problem. I take a second example, all right? So maximize z 3x1 13x2 subject to 2x1 plus 0. All right, still a small one, just 2 unknowns and 2 constraints. There's something new that will happen in this example that we'll talk about, all right? Okay, I'm going to clean up here. I will use this space to gather the information and analyze. Okay, let's put on the screen. Okay, so what I recommend you to do is between problems, you just close LP Assistant, or you have to keep track of the numbering, because if you start a problem now, it will start with number 8. It's a bit annoying, so I'll just close it. Do you want to save? No? Come on, just close for me. Close. All right, and I will start it again. And then start from 1, okay? You have to keep track of which tableau you want to use, right? It's kind of important. Okay, let's just go through this. So hopefully all this will make it easier when you do your homework. So I need a new variable, 2, 9, 1, 0, and 40. Is that right? The second equation is 11, -8, 1, 82, right? And the problem is maximizing. I need a minimization problem, so I need to make it all negative. Okay, and then let's declare the basic variables. Oops, is that right? x3, x4, yeah. Okay. So you are doing the regular simplex method for the first step. Just solve it. So this is a big negative number, and there's only one positive to click. Click. We shall be pro now. This is negative. The ratio is 9.2, 20, so that I will click. And now it's all positive. So I solved the original problem neglecting the integral constraint, right? So let's collect the information. So I have a first block. I get some information here. I have the C max. So this negative of this number is the solution for the minimization problem, but you're minimizing negative z, so this is actually the z max, right? I'll just take that to be my z max. So you have to do again this you probably can just hit on the calculator and you will get 58.4444, okay? So 58.44, that's 4/9, right? Is it 9? No, it's 5 down there. No, 54.8 then. So why did I say 9? 4/5. Okay, and x1 is 9 and 1/5, and x2 is 2 and 2/5. Or you can put what's important is this number, and you know there is the fractional part. Exactly what is the fractional part doesn't matter that much, all right? Okay, so what bound can we conclude from this computation? If I want to find the solution for the integer programming problem, what will the maximal solution be? Without that constraint, I have 58 point something. With the constraint, what's the best I could hope to get? 58. Do we all agree? Right? So you have a bound now. The max must be less than 58. That's the best you can hope for. Okay? Maybe smaller, but not bigger. Okay? Okay, let's branch out. So that's the first problem, and then let's branch out. You can pick either x1 or x2. Let's pick x2. It has a bigger fraction number, but it doesn't really matter. You can pick any one. Let's just, for the sake of vary a bit, let's pick x2 less than 2. And what should I put here? x2 bigger than, this is less than 2. This number is between 2 and 3, right? So the other one is the disjoint constraint, bigger than 3, right? So it exactly cuts that point out, and so you will have to find a new optimal solution. So let's draw these boxes again. So that will be problem 2, and that will be 3. And let's go and solve that. Okay. Hopefully, new problem from 1. That's the 2. That's the one we added x2 less than 2. So go to the editing mode, add a constraint, add a variable. So x2 is less than 2. So x2 here is less than 2, and I have a slack variable, right? And this x5 is a independent one. So now I have x2 here, meaning this is not pivoted. That's not canonical, so this is not basic. Is that okay? Let's go and pivot. So first step, get that basic variable. And then you see this b is negative, always happens. And then use the dual simplex. There's one negative number I will use. And now it's all positive. Okay, let's record. So what did I get? That's the Z max. If you write it out, if you can hit the calculator, that will be 52 point something. It's 8/11. If you do that, and x1 is 8/10. 10, 11, x2 is 2. Okay? That's what this says, right? Yeah. Okay, and then we have to do the table 3. You have to go back to problem 1 here, and starting from there. Always be careful, all right? So we need to add a constraint, add a variable, right? So this is x2 bigger than 3. So negative x2, negative 3, and that's the slack, okay? And set that one to be your basic, and remove x2 from the basic. Is that good? If you know what to do, it's very quick, right? And then pivot, and first I get the x2 back, and I get a negative here, and I get only one negative. I don't even need to switch to dual simplex. I know that's where I have to pivot. I can just click there. Now I have it all positive, right? Okay, so let's write down. So the that's 58.5 is the solution. So Z max is 58.5 at x1 is 6.5, x2 is 3. Now you have two tableaux. They both give you a non-integral solution. So which one do you think you should pick to continue? So if you continue with this problem, the problem further you will find the maximum will be less than 52. If you continue from this problem, the problem you further find, the maximum will be 58. I think that's more reasonable to start. I will probably get a higher maximum if I do there. Agree? So that's the rationale why I picked this one, okay? Because it has a bigger maximum. So okay, so that's picked. I'm going to branch out, right? So x1 is now my problem. So I do x1. It's between 6 and 7, so less than 6 and bigger than 7, right? So let me draw the blocks. 1 and 2. So that's table 4, and that's 5. Keep track. Keep track of which number, because you'll be so happy that you did that. All right. So I have to go to table 3 to continue following my chart. Is that right? So table 3 is right here. Okay, bring this to the top, and then I do a new one from table 3. Okay? So add a constraint, add a variable. All right? So what constraint am I adding? x1 less than 6. So x1 less than 6. And I put in the basic variable. And then what should I remember to do before I continue? I need to remove this x1 because it's not basic. Is that right? Okay, it's the same thing, but you have to be able to do it. Okay, now we pivot. We claim the basic variable back. And now I need to do the dual simplex. And you see the new one you added has a negative b. So check the ratio, negative 0.1, 0.3, so that will be chosen, right? And I click there. And then it's all positive. So I solved it. Let's record. That is in table 4. Table 4 gives me Z max. What is that? 58, 4/9, if you write that out. x1 is 6, x2 is 3, and 1, 9. So it's not integral, okay? But I have some solution there. Okay, and then we have to solve the other half of the branch. Now you have to go back and find table 3 and start a problem from there. Right? Is it all clear for us? It's repetitive, but you know, you need to be able to keep track of all things. Add a constraint, add a variable, right? So what am I adding? X1 is bigger than 7, so it's negative X1 is less than negative 7. That's what I add, right? And this is X6. So I always have to remember X1 now is not basic. Okay? So now I pivot. I claim it back to be my basic. Okay. Now you see this is negative. And then I should use the dual to pivot here, but I don't see anything negative here. So what does that mean? We had that before. That's not feasible. Is that clear? Now there's only one choice to branch out, that is this one, right? It's very clear. Now let's branch out from here. X2 now lies between 3 and 4. So X2 less than 3, X2 bigger than 4. Is that right? Okay, so let's work. All right, 5. So this will be table 6, and this will be table 7. Keeping track. Okay, let's. Okay, so I need to go and dig out table 4. Is that right? Where is it? It's hiding under all these piles. There you go. That's the one I want. Now I'm going to start from there. All right? Go problem, start from 4. All right? That will be my 6. And what do I add in is X2 less than 3. So add it. New constraint, new variable. X2 is less than 3. Is that right? So declare your basic variable. And now you know the one that has X2 is not basic. Is it all clear? All right, so you just need to know where to click. And then you just click and it solves it for you. So claim this one back. Now you see I have a negative number and I need to pivot. And there's only one negative, so I'll pivot here. Oh, what nice integers. They're all integers, very nice. So let's write down. 57 is my Z. Z max is 57. That looks like a very nice candidate. X1 is 6, X2 is 3. I know the maximum shall be less than 58. This is just one less. It's really close. So that could be so. But we still have to solve the other half of the branch to make sure. So I need to go back to table 4. I thought it was under here, right? So you need to know which table to look for, right? Table 4. And let's start a new problem from there. That will be table 7. And go to editing mode. Add a constraint, add a variable, right? So what we're adding is X2 is bigger than 4, meaning negative X2 is less than negative 4. Is that right? Okay, and put that variable. And you have to remove the Y2 because that's the one you did. That's not basic. Okay, let's pivot. Let's first claim this back to be the basic. So I have Y2. And now you see, come on, show me cleanly. Now you see that this is negative, right? Using the dual simplex, I pivot. There's only one negative number. That's where I click. Wow, look at all these nice integers. Let's record it. Okay, so I'll come back to that tableau one more time. So we do see some fraction numbers, but they are at not important locations. So what we found is I have a Z max equal 58, obtain add. All I need to make sure is X1 and X2 are integers. Okay, all the others are slack variables. Okay, if they don't take integer value, that is fine. Okay, so that is my comment. So let's draw down that tableau that we actually have this good answer here. This is the final tableau, and you see y1, y2 takes an integer value. But some of these coefficients in front of y3 and y7, these are slack variables. They don't take integer values, and these coefficients are not integer, but they don't matter. All that matters is if these two are integer, then the final answer will be integer, because we have all integer coefficients, right? We're talking about pure integer problems, okay? If your coefficients for your original problem are not integer with fractions or whatever, then none of this would work, okay? So that's the restriction. Okay, so that's my comment. Okay, now we have two solutions from 6 and 7. They are both integers. All the solutions are integers. So do you think I can conclude now? Have I found the optimal? This one, is that right? I found 58, where actually I know that's the best I can hope for from the first step, right? So that is your optimal solution. You want to give me a reason, because I know I have the bound. The bound says max must be less than 58, and I find the best possible. It's just exactly 58. And then I stop. Is that okay? All clear? Any questions? There will be homework problems like this. You have to open up LP Assistant by your side and work through and label and keep track of everything and produce that branch and write down the bounds that you get. Question?
When we're doing our homework, do we have to like print out or send in all of the LP assistants we did then?
Yeah, I would think so. It would be much easier for me to see if you made some mistakes, because you claim I have this, and then it's wrong, and I don't know what you did wrong. But then if you give me that, then I will see where you did wrong, right? Yeah. You can take screenshots and put multiple files on one page and print it. Yeah. As you see, it does have the option for you to save everything. You could save all this bunch into a folder called that problem, and then later on you open LP Assistance, you can open all these problems and go back and look at them if you want. Yeah, but yeah. Okay, any more questions? Let's just say purely hypothetical. Let me ask a question. As I was solving here, I picked this to branch out. Let's say purely hypothetical. Over here, I find Z max equal 50, and here I find Z max equal 51. And they're all integers. Do you think I can stop or I cannot? What should I do? Why do I pick 50, 51? What was I thinking? As against the 52 you got there. Is that right? So we picked this one because the problem down here, the Z max will be less than 58. And if you pick this one, all those branch out, the Z max will be less than 52. But if you shall be unlucky, down here you find this max is 50, this is 51. You cannot claim that's your solution. Then you have to go and branch that out and figure out what you get there. Is that clear? It's very annoying. Not something you want to go and impress someone. Say, I can solve it. Look, and then there's so much to do. Okay, you lose patience. So, all right, but let's hope that will not be the case that we will encounter. So that's all. All right. No more questions? Then I close up all that, and we have an introduction to the next topic. All right. Just a brief introduction. Won't have time to go into the detail. So, chapter 7. Oh yeah, I want to say one more thing. So I showed you how to do this using LP Assistant, and you manually decide, right? There's a lot of intelligence from you. You are the master to click and to make new problems. And if you use Excel, it actually can do that all for you. It's a black box. You set up as the way we set it up, and then there is an option. You just need to select that you want your solution to be integers, and you solve it, and it will do it. Is that okay? So I'm not going to even open Excel and show you. You're curious, you can go open it up and play with it, and that's all, right? You can just choose to be integer. Okay. All right. So here is a chapter that we will be revisiting a old problem, not old problem, transportation problem. It's one type of problem that we talked about when we were doing the modeling. The problem that is like you have certain number of warehouses and you want to distribute the goods into certain retail stores, right? And then each warehouse has limited amount of supply, and each retail store, whatever distributor, will have some demand, need at least so many of them. And then there'll be cost of shipping, whatever, and how do you solve it? How do you set up the problem? Do we remember all that? You remember? So the variable that you set up for the problem, xij, is the amount shipping from source I to destination j. Is that right? And for all ij's. So that is the problem with tons of variables, right? So what we were talking about here would be even make it worse, we will be looking at really large-scale problems, meaning I have many warehouses and many retail stores. And let's just take a simple example just to have an idea that it can get really nasty. So let's say I have 100 warehouses. And then I have 300 stores, retails, and I need to ship things to the stores so they can sell, right? So by setting up the problem, your xij, I takes value from 1 to 100, j takes value from 1 to 300. What will be the number of unknowns, variables? Isn't that 100 times 300? Is that right? That will give me 30,000. I need to find values for 30,000 variables. And what will be the number of constraints? Well, so far we have the limited source from the warehouse. That gives me 100. And then demand from the store, that gave me 300. So you add that up, you get at least 400 constraints. Is that right? Say maybe Walmart is facing something like that scale to solve. That's really huge. Okay, so you want maybe something more efficient than just the regular simplex method to deal with this particular problem. Okay, so just to get an idea. So before we get into that, we'll talk a related problem, a distribution problem. Okay, I'll set it up. Okay, so let's set up some numbers. So let's say M. That will be the number of warehouse. We call these origins. So you want to move things from original location, a bunch of them, to some final destination, okay? And then n will be the number of destination. Okay. And then I have some supply. AI will be supply at ith origin. And then I have demand from retail, so demand at jth destination. So that's all set up. And then here there is an additional thing that we're going to add into it, that is to connect origin I to destination j. Say you run a truck. The truck has maximum load you can put onto it. You cannot exceed it. So there will be a max amount you can ship from I to j. Okay? So further constraint. So max amount can be shipped from ith origin to jth destination. Okay, so that gives you new constraints, a lot of them. Okay, and then that's our variable. We'll define now xij. That's like a schedule that you will set up, right? How much you're going to ship from I to j. That's this x. Okay, so amount shipped from ith origin to jth destination. Okay, so let's set up the model for this. We're not trying to optimize anything here yet. What we want to do is just set up all these constraints and see if we can find a schedule that will satisfy all the constraints. Okay, and then the optimization part comes later. Okay, so what does this lead to? To what constraints we have? We actually have a bunch of them. So the first will be on supply constraint. So coming from supplies, because from the ith origin, this is that much you can ship out, right? So what will be the total amount you will ship out from the ith origin? That will be xij, and you sum over all j's, all different destinations it's shipping to. Does that make sense? So j from 1 to destination n. Okay, that has to be less than a, no, ai, yeah. Okay, and this holds, you have to go through all the origins, 1, 2, 3, I, all the way to m of these constraints, right? Okay, and then you have also constraint from the demand, because you have to ship that much to the destination, j. So what will be the total amount being shipped to destination, j? Well, that will be adding all this up for all different i's coming from different warehouses, right? So I from 1 to m, and that has to be bigger than bj. You have to have at least that much, right? That's what the store demands. Okay, and then this holds for j from 1 to n. So you have m plus n constraints already. And then there is also the constraint that maximum load can be shipped from I to J, right? So this is a transportation limit, right? What would you call that? Shipping capacity. So xij must be less than this kij, and it's also non-negative. Okay? And this holds for all I from 1 to m and j from 1 to n, any pairs. So this actually gives you m times n constraints right here, tons of them. So overall, a lot of constraints. Is that clear? So if you set this up, say m and n are 10, for example, then you have 10 equation here, 10 equation here, 100 equation here. You have 120 equation. Probably you can't even type that big a tableau in the LP assistant, right? It's too much. So some other methods will be designed to do this, okay? So before we get into any of these, let's just look at this. Now, so the goal here is not to solve. The goal for this discussion is to find a shipping schedule that's feasible, meaning all the constraints will be satisfied, okay? All these 120 equations will hold, inequalities will hold, okay? So before you get into that, we can think a little bit about it. I have supplies at the origin, I have demand at the destination, and this must be satisfied by bigger than equal sign, and this is, I cannot ship out more than that. So if the total amount of supply shall be less than the total amount of demand, then I cannot solve the problem. Is that right? This is solvable if my supply is bigger than the demand. Otherwise, all these inequalities will not hold. Okay, so make that observation. We must have, what do you have? What do you have to say? So total supply shall be bigger than total demand. Okay, so writing it out into what we have, the notations we have. So total supply will be adding up all the AIs over I, and that shall be bigger than adding up all the BJs over all the J's. Okay. If that doesn't hold, then it's not feasible. Then you don't need to solve it. It's a wrong problem. Is that clear? Okay. And then also pay attention. So here we are not solving an optimization problem, okay? So just to stress. So this right now is not an optimization problem. We are just trying to find a feasible solution to all the constraints. That's what we're trying to do. Because the constraints are so huge, to find one feasible schedule becomes already non-trivial. All right, and you need to start from there, then you can talk about optimizing over the set of feasible solutions. Is that clear? So what you do will be you set up, so the idea of how to do this, which I'll just briefly say it, we'll get into the next time. You will have to go through some kind of a iteration. It's actually not really well-defined iteration. So you do like this. You look at your, you can go through with in the order as your index. let's say I can start with origin I equal 1 and to see how much I should ship to each of the destination that satisfies the constraint. Okay? Usually that row you can easily do. And then you go to row 2 and you go to row 3 and you continue. And then you will check at some point some constraints cannot be met anymore, because that's not the best schedule to start with, right? Not just satisfying the first. And then you go back and then keep adjusting, keep changing, and hoping that eventually you find one that fits. Okay, there will be chain reactions happening if you adjust, and we'll look at those next time. Okay. Any questions?